Ladies and gentlemen, we are on to chapter 8, Strings and Serialization. We're about to close the semester, so I announced, I believe, that these notes were ready, but I didn't get around to preparing a video on them, but here it goes. So we'll be covering the following topics according to the book. The complexities of strings, bytes and byte arrays, ins and outs of string formatting, a few ways to serialize data, the mysterious regular expression. So I gave you a link to the Python style guide. So this is another thing that you should check out if you are, uh, interested in how styling should be in your Python programs. So I have a function that I'm going to be using later on. So this is for printing columns. I think we've done this before, but anyway. Strings are immutable, as you know, which means you cannot change any part of a string, individual characters or or slices. So Python does not distinguish between individual characters and multi-character sequences or strings. A single character is a string of length 1. So there is no difference between characters and strings. Only that we should know that individual items in strings are characters. That's all. So Python 3 represents all characters from all kinds of spoken languages using Unicode, which is a character definition standard that can represent any character in any language or any character in general. So we have actually a link. So this link says Unicode is a universal character encoding standard. It defines the way individual characters are represented in text files, web pages, and other types of documents. Unlike ASCII, which was designed to represent only basic English characters, Unicode was designed to support characters from all languages around the world. The standard ASCII character set only supports 128 characters, while Unicode can support roughly 1,000,000 characters. While ASCII only uses 1 byte to represent each character, Unicode supports up to 4 bytes for each character. So it's a varying. It's using a variable number of bytes depending. There are several different types of Unicode encodings. Though UTF-8 and UTF-16 are the most common. UTF-8 has become the standard character encoding used on the web. It is also the default encoding used by many software programs. While UTF-8 supports up to 4 bytes per character, it would be inefficient to use 4 bytes to represent frequently used characters. Therefore, UTF-8 uses only 1 byte to represent common characters, like those that are in the ASCII code as well. European, Hebrew, and Arabic characters are represented with 2 bytes, while 3 bytes are used to represent Chinese, Japanese, Korean, and other Asian characters. Additional Unicode characters can be represented with 4 bytes. So let me just fix a little mistake here. So UTF-8 is a variable with character encoding scheme. There are characters that are represented with a single byte, and there are others that require multi-characters, or multi-bytes actually. Actually, I should have said multiple bytes here, even though it means the same thing. UTF-8 is backward compatible with ASCII because the first 128 characters of ASCII are mapped identically with or using UTF-8. Or actually, let's say in UTF-8. So here's a reference as well. So we can define strings, as you know, in 3 ways: single-coded strings, double-coded strings, and then we have triple-coded strings, or which means they are multi-line. And actually, we can even do the same thing using single quotes. Wouldn't matter actually. So even if I'm using single quotes, it would have been the same thing. So whatever I can do with double quotes, I can do with single quotes. They are all strings. So actually then it would be, so let's actually just say that this is 4 ways, just to be consistent with so there are two general ways. One, single line strings, and then multi-line strings. That's the two basic type actually. So a given type of string can hold strings of the other two types without escaping. So you can just do it this way, so you can have a single quoted string and then use double quotes, or you can have a double quoted string using, you can have single quoted portions, even though it's not anything different. So you gotta basically quote character and then all the other characters. So it doesn't really matter. It's just for visual effect. So we can escape using backward slash and include both type of quotation characters as well. So we can do it as so we can use anything with it, anything. So you could just do a double quoted string with double quoted substrings, let's say. So this would actually be this is a code thing. So you see it's fine, and we can see that we have, this gets turned into a single quoted string, but this is just for displaying anyway. So we can see that we have the double quoted string is, or like you can think of it as a substring inside the other string. Now you know all about iteration, indexing, and slicing, as well as concatenation. So we can loop through individual items in a string, because a string is a sequence. So we get individual characters, we just print those out. And then we have indexing, then we have slicing, we have concatenation, and we can check whether string contains only digits, whether it's a decimal, but we need to find out. So we have decimal characters, essentially not floating point value kind of decimal. So 104 or characters 104 would be decimal. Numeric, not numeric. Again, it's not checking whether this is in floating point format. So unfortunately, the period character we use to construct floats is not recognized as part of a decimal number, because another character is used for that purpose. And that's just this middle dot. So it's a little kind of strange, but anyway, just a little tidbit there. So when we try conversion, the conversion fails. So this is D, though. When we do D, we get something funny. We're supposed to have 45.2. We get 4502 or 4502, and we convert this, we get the integer value. And this means that the middle dot character that's used gets converted to 0. But if you say it's decimal, you get true. See, but that's the way it is. We can check this is whether this is a digit, it's false, and so on. We can check the index of a slice or a character. So we have index checking from the left side, and we have our index checking from the right side, or reverse index. So we get because we have two different L's, so we get the indices for those. If we check for the index of a non-occurring character, we get a value error. But if we do the same with find, we instead get -1, which means the letter is not in that string, and you don't get any exceptions raised. So negative values in find mean that you do not find the letter. It doesn't mean it's -1 the index and it's the last character. It doesn't mean that. So here are the methods and fields that are available in the string class. So I just wrote something really simple, just to leave everything out with double underscores. Everything else is basically public API. So we have all these, and you should be familiar with all these things. So all string class methods return a copy of the string or part of the string depending on the method, but none of them modifies the original string since the string type is immutable. So we have this quote from Mark Twain that says, "Never regret anything that made you smile." So we split, which means we split by space. And let's see here. If we partition with single space, we get basically we are partitioning the string into two with a single space. So anytime you see the single space, that's where you cut it into two. So if you look at the string partition method, this is what it does. So it's a little different from splitting. So it partitions the string into three parts. The first part, the partition string itself, and the rest of the string. So we have excellent sites for string formatting. I think I have announced these before. You should check these out. Not just simply read them, but you should learn the stuff in them because they're extensive. And this is essentially the subject matter of ecc102. So I don't get into, I don't go in and tell you guys exactly the same things again, but I will go through some of these. So Python 3 introduced format strings or F strings, which make life quite easy in many cases. So we can format strings in three ways using the old string modulo operator, So this is like C-like, C++ like format. You put that format down in a string, then modulo operator, and then the list of, or a couple of values that would match these placeholders. We could use string format in various ways, but essentially, using this kind of format with braces. Again, the same kind of specification, goes for these because these are all, powerful ways of expressing how values should be formatted. So it's brought over to the string format approach. But using F strings, we actually do everything within the string, even if we need to call functions or methods or do slicing on strings or access fields in an object. We just do it all within the string, and we start the string with a lowercase f. So if you have number items, you just mention it here, you'll get replaced. And then actually, this is unformatted. It just basically means put it in place of this format specification. But as you can tell from here, we can actually do a dot to f just like we did here and get the exact same thing, because here we have no formatting, and dot to f format. So we just repeat the same thing. So let's just see how these things work. They'll all work the same way. So if these values are coming from some variables, you could just simply do the whole thing within the format string. So we can refer to variables already defined within a scope from within the format string. We can even run functions or methods, just like I said. So they will start with an F prefix. Let's just put a little dash here. So let's define a useless class that defines a few interfaces that we can call from within an F string below. So we have format test, and should bring this up. So we have x and y. Y has a default value. We have a method that's called method. It just will display that it was called. str prints format test represent actual calls str. Len returns 5 unconditionally. Get item returns 9 unconditionally. So here we have format test initialized with 3, so y would be defaulting to 88. So we can say welcome to ft, which is the format test object, and we can just call length and access ft, and then use the square bracketed um, format to get some, to specify some indexing, but it's going to be, be activating this function get item, call method on it, and then access individual instance variables. So it would just work like that. You see, so length is 5 because let me see, length will always return 5 unconditionally. So it's not really meaningful, but anyway, it's just, and then the get item would always return 9 no matter what you ask, whatever you specify in the index, as long as that's an integer value. But it doesn't really matter. We don't even care about what the index value is. And then we call format method, a method in the class, and then we get the string that it produces and so on. So you can see the x value and then the y value. So what if we wish to display braces as part of our format string? Well, we just specify the braces twice. So brace will just look like a brace in the output. Whether it's a closed brace or open brace doesn't really matter. So suppose we wish to adjust our output format according to the width of the longest string. This means that we would have to create our own formatting string first before we can use that formatting string to print values onto the screen. So where we see the double braces, the brace enclosing and so on. So let's just clean up the sentence from all non-alphabetic characters except for blanks and end-of-line characters. So I'm running through this thing. So we end up with this. See? So suppose we wish to tabulate each word from the above sentence in the first column along with its length in the second column. Of course, we can guess as to how wide the first column needs to be, but there is no need to do this. We can just map length onto the words. So I want to print all these words, but I want to format them, and I need to figure out what's the longest string is. So I just found that. So I map length on all the words, and I just use max to get the maximum length. So I'm going to have so the longest word here has 11 characters. So here is the format string. So I have maximum length s right here within. This is the actual format for the string itself. Then, but I'm using double braces so that I don't, we don't activate these. But then I need to put in the maximum length inside this thing. So I'm using keyword arguments to put this inside using a string format. As you can tell, I'm using format. And there is nothing here. In the second one, I'm just going to put the length value. So format would look like that. You see? That's why I need to use double braces so that they don't get treated as placeholders for values. And so this is going to be treated as a placeholder, obviously, because I don't have double braces around it. So I'm going to be putting the maximum length inside. There would be 11. So I would be formatting this thing with 11s. So 11 spaces would be reserved to display all the words. So if I just simply use this, I get the title, print some lines and all these things. So I'm going to run through this thing and then print each word, and then print the length of the word right next to it. So here we go. So I wanted nice columns, right? So I wanted to print string in the first column and the length in the second column. So the length value could be very long, whatever. But if I want these things aligned like this, I need to figure out how many spaces I should use to display all these. If I don't do that, everything would be jagged and it would be looking ugly. But now we can tell, here's the longest, the word with 11 characters. We could add more if I wanted, a little bit more space in between two columns, but that's just very easy to do. So this is how we would do things actually if you want, perfect alignment for any kind of data. Well, what if we wanted to do right alignment? Well, the default alignment is to the left for strings at least. So what I would have to do is use this character that means right align. So it's the same kind of format string, and actually I should display that as well so you can see it. So here it is. So it would be looking like that. So I just left some more spaces in between. And then I would be using the, actually I should have done, instead of putting this thing down, I should have used fmtra here to format the title, because I want to use the same exact thing for the title. I think I did the same thing here as well. I just picked this up instead of using the automatically generated version. So let's just do this again. So it would work the same way anyway. And let's go. So we got the same thing here, except here we have more space. But then you can see that the title is using right alignment as well, as well as the column data. You see. So here is another example of formatting. All kinds of things in here so that we can nicely align the data that we have. You can take a look at the details of this. So we are using tennis for everything, and that's pretty much it actually. Here is you get a nice printout. We can shorten values any way we wish. So see how we use the first four letters of each product in the first column. So this is a different version of it. So, I just wanted to cut it out. So if you have long names, you can just chop them up if you want to. And the thing is, you see, I'm chopping the product name right here using slicing. I am centering the quantity value with 10 spaces. I am left aligning the price with dot two, so with two decimal places, and I'm printing that subtotal in the default formatting, which would be right alignment for numbers. So this is what I would get. Again, it looks pretty nice, but this is just to show you that I can chop things up. I don't have to print everything. If it's going to take very many characters, so it will occupy the whole screen. Let's say for a column, I can chop it up to still make something meaningful out of, to actually create a meaningful table. Then we have custom formatters, so we can use custom formatters for datetime, objects defined by datetime strftime function. We can write custom formatters for objects that we create. So this beyond the scope of the book, so we're not going to get into that. So we can use __ format or implement this one to get this special formatting. Print formatting will not always be sufficient for printing things out. For example, print formatting capabilities fall short when we want to do templating, as when we need to generate HTML pages. In those cases, we need to look into using templating libraries, not print formatting or string formatting. It would fall short. But it's not meant to do everything anyway. But it's still very powerful as long as we use it for the purpose, for the intended purpose. So there will be instances where you will be unable to use f-strings. So you cannot use an f-string template with different variables. In addition, f-strings have been introduced in Python 3.6. So if you're using an older version of Python, you're out of luck with f-strings. F-strings and str format share their specifications, so it's quite easy to switch between the two. I started using F-strings quite a bit, as you may be able to tell. You should prefer F-strings whenever you can use them. When F-strings, with F-strings, there is no need to pass arguments as in string format, so it takes less to write a print call. And there's only one place to look at as far as printing the value of a given value is concerned. That is, you need to look at the format specifier and check whether your parameter order matches the format specifier you intend for the parameter. So with f strings, we specify which variable we want to print along with the format we wish to use, all in one place in our code. They are all right next to each other. So you can tell from here, I got this product is the name of my variable. I want to slice it, and then colon, then followed by the format I should use for the value, and then same for the other ones. So let's take a look at Unicode strings. So we have an uppercase I, which we use in Turkish, and it's used in other languages as well. So if we take the ordinal value of that character, we get 304, way beyond ASCII. Then we have the C with with a Cedilla. So that's ch in Turkish, and it's used in other languages as well. That has the ordinal value 231. Uppercase U with umlauts, or Ü in Turkish. Again, it's used in other languages as well. That has the ordinal value 220. Greek capital letter omega has the ordinal value 937. So we can actually convert this value to binary by calling bin. We can check the ordinal value of this particular character, like a text bullet. That's 8,226. Let's check out the euro sign. That's 8,364. We can convert it to binary character as well. We're gonna see we're gonna do some exercise about these in just a bit. So if I encode the euro character as UTF-8, convert it to bytes, we get that. So we can see how many bytes. 1, 2, 3. So X it means that it's hexadecimal. So you get two digits, two hexadecimal digits, two more, and then two more. So each hexadecimal digit actually represent 4 bits. So 4 plus 4, 8 bits, 8 bits, 8 bits. So we have 3 bytes actually represent. So to represent the euro character or euro symbol, UTF-8 or Unicode uses 3 bytes. I can do this formatting with B. So this code point euro means that it's the ordinal value essentially. So I can convert it to binary. This is what I would get. I can convert it to hexadecimal. This is what I would get. So 20 AC, right? Now, so you should read about the UTF-8 from the page. So we're going to look into how we represent characters actually using UTF-8. So if the bits for code point are up to 7, so if you're up to 7 bits, you are within this range of code points, and you represent your first byte starting with a 0. So the first 0 means that you're representing a character actually that's going to be represented with 7 bits. So this means ASCII actually. Now this is for a single byte representation. So if you are actually using the Unicode representation, and you see a character that starts with a 0, that just means one thing. It means that it's actually an ASCII character, and you can just look at the remaining 7 bits, and that's your character, and that's it. Then bits for if you are all the way up to or between 8 and 11 bits. So if you need that many bits to represent your character, you are going to use 2 bytes. And the first byte will start with a 110, and the second byte would start with a 10, and the remaining bits would be used to represent the particular character that fits in 2 bytes. Actually, you can tell here that we have 8 bytes here, 8 bits here, so I have 5 bits remaining from this, and then 6 bits remaining from this, right? So total 11 bits. So everything above 7 bits I'm going to use to represent using 2 bytes. Well, similar thing goes for 3 bytes and 4 bytes. So the first byte of a 3 byte Unicode character starts with a 1110. Then remaining bytes, we know that this is going to be a 3 byte Unicode character. So I'm essentially encoding that information in the very first byte. So if something starts with a 1110, that's a 3 byte Unicode character. So whatever remains of the first byte, which are 4 bits, are going to be used to represent the value. Then the next byte will start with 10, and the next byte will start also with 10. So 6 bits from here, 6 bits from here, that's 12 plus 4, that's 16 bits available to me to represent my character. So 4 bytes goes similarly, so I have another one, so I have 4 ones and a 0. So if my Unicode character starts with 4 ones and a 0, this is of course in binary, I know that I have a 4 byte Unicode character. No other Unicode character will ever start with 4 ones and a 0. Okay, so these are unique. That's why you can actually recognize the actual sub-format, I should say, as far as the the indication of how many bytes we need to use for a certain character is concerned with this scheme. And then remaining bytes will always start with a 10, 10, 10. So we have 6 bits available from this byte, 6 bits from this one, 6 bits from this one, that makes 18, 3 more, 21 bits available to represent my character. So UTF-8 is a multi-byte character encoding scheme. Every character is associated with an integer number, which is called a code point for the character. You can think of this as the ordinal value. The code point for a character determines how many bytes will be needed to represent that character in UTF-8 format. All 8 bits in a byte are never used, as you can tell from this format here, right? You see, these are all encoding bits, but they are not used to represent the actual character. The bits in place of X's here are going to be used to represent the character. So because the set of initial bits in every byte are reserved to encode what kind of byte we're looking at. So we talked about these things, but let's just take a look at these things in more detail. A character, so we have leading bytes that start a character representation. A character that only needs up to 7 bits, to be represented always starts with a 0. Nothing else starts with a 0, right? Only this one starts with a 0. No, remaining bytes also start with a 0. Nothing ever starts with a 10 except these later bytes. See? So leading bytes start with a 0. Leading by starting with a 0 always indicates a 1 byte Unicode character. If something starts with a 110, that's a 2 byte, and so on. So a character, therefore, the highest code point that can be represented with such a byte is 2 to the 7 minus 1, since we start with 0. So this 127. So the character with the ordinal value 127 would be represented using a single byte. For a 2-byte character, the first byte, that is the leading byte, starts with 110. 1 bits indicating that we have a 2-byte character, and a 0 is also required. Since we lose 3 bits from the leading byte and 2 more bits from the continuation byte, so these other ones are continuation bytes, We have a total of 11 bits that we can use to represent code points. So the highest code point we can represent with a 2-byte UTF is 2 to the 11 minus 1. That's 2047. 2 to the 10 is 1048, as you know. So multiply that by 2. I'm sorry, 2 to the 10 is 1048. 1024, I'm sorry. And 2 to the 11 is basically 2 times that. So this 2048. So minus 1, 2047. For a 3-byte character, the first byte, that is the leading byte, starts with 1110, indicating that we have a 3-byte character, and a 0 is also required. We lose 4 bits from the leading byte and 2 more bits from the other ones, so we end up with 16 bits available for us to use to represent a UTF-8 character. So that's so we have code, so we can support code points up to 65,535. For a 4-byte character, the first byte starts with 1111, 4 ones and a 0. Since we lost 5 bits from the leading byte and 2 more bits from each of the 3 continuation bytes, we get we get 21 bits available. So 2 to the 21 minus 1 gets you 2 million something. So that's a lot of characters we can actually represent. So continuation bytes always start with 10 if the character requires at least 2 bytes, as we have seen. So see, 2 bytes, 3 bytes, 4 bytes, they always start with. So these are continuation bytes, they always start with 10. Therefore, only some of the bits in each byte can be used to store the code point for a given character. These bits are shown with X's in the above figure, as I indicated. So here's an example. Represent the euro sign in UTF-8 at byte level. So we're going to look deeper into how we do this representation. So we have some functions here that will tell us how many UTF bytes we're going to need. So if we encode the character like we have done before, actually, and if you take the length of those bytes you get, that's the number of UTF bytes you're going to need. And I want to just remind you what we did. If you remember this one here, you see, those are the, so I can encode my character in UTF-8 and I turn it into bytes. I could just take the length of it and I would get 3. And let's just do it here like this. You see, so I would get 3 bytes back. So I know that to represent the euro character, I need 3 bytes in UTF-8. And then I can just easily, I've done this above, so I use the B formatter to convert an integer value to binary without the 0 at the beginning. So I can just take the length of that and I can tell how many binary bits I would need. So let's take a look at this. I would need 14 binary bits to represent the code point of the euro character. Number of bytes. Oops, I should define these. 3 bytes, right? So I can just show you what I showed you above. So this is the binary representation, and we can just count these are 14 bits. So we need to group these things into chunks of 4. So here is my binary value, and I'm going to convert it to hexadecimal. So I have 110, then I have 1010, then I have 4 zeros, then I have a 10. But I want to just complete it so that it's a full 4-bit representation in each of these chunks. So we got a total of 16 bits, right? So the first one would be actually 2, right? Because this is in hexadecimal would be 2, which then we have a 0, we get a 10, that's A, we get a 12, that's a C, right? This is binary 2, binary 0, um, binary, value of 10, binary 12. So we have 20AC. So therefore, the code point for the euro sign is 0x, which indicates the value to be hexadecimal, 20AC in hexadecimal. So the next question is, which bits will go into which bytes? So obviously, Python tells us we're going to represent this using 3 bytes, but what will be the exact bit representation or bit layout of these things? We need to start from the last continuation byte. Note that each continuation byte has only 6 bits for the representation of UTF character. So the last 6 bits in the above binary value will go into continuation byte number 2. So we take the last 6 bits and place it into the continuation byte. So this means we have 12 bits remaining. The next 6 bits will go to the second continuation byte, right? You remember that we have this situation. We have 6 bits available here, 6 bits available here, then we're going to have 4 bits remaining. So that would be a total of 16 bits. And then we only have 4 bits that will go into the leading byte, so that's how it will we chopped up, right? So we know that the last continuation byte would start with a 1 0. The one before that would be also a continuation byte, would start with a 1 0. And the first byte would be the leading byte, which would indicate that we are using 3 bytes. So we have 3 ones followed by a 0. So the 1 0 1 1 0 0 would go here, as you can tell. The first 6 bytes, 6 bits, I'm sorry. The second 6 bits here would be these, and the remaining 4 bits would be here. So that would be my UTF-8 representation of the euro character. Of course, this is done for you automatically, but we are trying to understand here how this all works, how actually UTF-8 works. So the hexadecimal value here, this whole thing, is the first 2 is E, because that's 15. I'm sorry, that's 14. Then we get a 2. Then we get an 8, because we're chunking these things in 4-bit chunks, right? This whole big thing here. Then we have a 2, then we have an A, and then we have a C. Finally, we got how the euro sign would be laid out in 3 bytes in UTF-8 encoding given its code point. So do not forget that the euro sign has the following code point in hexadecimal. See? This is the code point. It's different from its bit layout in UTF-8. So let's write the euro sign character to an output file. So what I'm writing is the character euro, and I want to do a hex dump on this thing. Lo and behold, you see what we get? We get an E282 AC. Actually, I could just, before that, I could just simply do a cat on this file. Oops, data, euro character. See, that's the euro character. But if I get a hex dump, I get how its individual bytes would look like. So here with the cat I get a visual. With the hex dump I get exactly what's inside. So I get an E282 AC. What did we find? We found an E282 AC. So so we perfectly applied the technique of UTF-8 representation, and we got the same thing as what the system does for us. So from the hex dump above, we see that the byte layout of the euro sign is identical to what we worked out. It's E282AC in hex. We can also observe that the file only contains 3 bytes, which are those of the euro sign, because that's all we have written in there. And how we can tell is very easy. You can see the value here. So we stop at byte index 3, because we have bytes 0, 1, 2, and there's nothing for 3. So we have 3 bytes here. And you can tell here that the hex dump doesn't give you any byte-based representation because these bytes don't have any visual representation. So in summary, another way to read the above table is as follows. Code points that require 0 to 7 bits will require a single byte. 8 to 11 bits will require 2 bytes. 12 to 16 bits will require 3 bytes. 17 to 21 bits will require 4 bytes in UTF-8 encoding. Since the euro sign required 14 bits, we are in the 12 to 16 bit range, obviously, so we will fall in the 3 byte region of UTF-8. So we have some more examples that require 1, 2, 3, or 4 bytes. Again, distinguish between the code point for a character and how the bits of that code point are laid out with extra mandatory bits in leading and continuation bytes when represented as UTF. So we have some examples here. So you can take a look at these on your own, but it just follows exactly what we did. And it's actually a simple procedure when you think about it in terms of how we did things. So we have the list of ASCII characters anyway. So that would be the same as the regular ASCII. Now, converting bytes to text using strdecode method. So we have some characters in here that we cannot make out anyway. This is in binary format, but we have written hexadecimal style. When we write this thing, we get cliche. Actually, this is going to be cliche, the word cliche anyway. But this last thing doesn't have any visual representation, so it's left as it is. So the characters that's outside the ASCII range remains in the escaped hexadecimal format, which is xe9. In addition, the B prefix tells us that the representation is still in, it's not binary, but it's in bytes, and it's not a string, it's just bytes. So we have 1, 2, 3, 4, 5, 6 bytes. 1, 2, 3, 4, 5. The sixth byte doesn't have any visual representation. So what if we decode this thing as Latin 1? We get cliche, E with the thing on top. Well, let's try different encoding. Let's say the Cyrillic encoding ISO 8859-5. Well, we get something totally different. So the xe9 at the end in characters variable maps to a different character in the Cyrillic encoding, compared to the Latin 1 encoding. Oops, this somehow doesn't work. I should have done it like that. Yes, okay. If we need to convert incoming bytes to Unicode, we are clearly also going to have situations where we convert outgoing Unicode into byte sequences. This is done with encode method, which, like the decode method, requires a character set. The following code creates a Unicode string and encodes it in different character sets. So we got cliche in the variable characters, encode as UTF-8, we get that. Encode that as Latin 1, we got that. And then we have it as another, character, and then we get that. And if we try ASCII, we get an error because this E9 character cannot be handled by ASCII because there is no ASCII equivalent, visual representation. So actually, the reason is that ordinal value is not in the range. So it's not in range 128, which means the value is beyond 0 through 127. So repeat the problematic last encoding statement and pass errors ignore to encode. So let's just do this. So we're telling just ignore the errors, and let's see what we're gonna get. We get basically that the character being ignored totally. But there is no encoding, so there is no failure. So we can do replace. So we replace it with a question mark, and so we have also errors, XML replace. So anyway, we have other kinds of replacements. So we're replacing XML character um, reference replace. So we get that value represented with XML or HTML actually. So it would be the HTML version of it. But anyway, so we know that strings are immutable, but we have byte arrays that are like strings that are mutable. So they are mutable strings. The bytes that represent the bytes data type is immutable like the string data type. Indexing and slicing can also be used on byte objects. There are instances where immutable data types such as byte or string will be impractical to use. For example, if we are reading messages from a socket, we may need several receive calls to complete the reception of a particular message. In such cases, using the byte array data type would be useful because byte arrays are mutable. Byte arrays are like lists, except for the fact that each individual item in a byte array is a single byte. It's just like the string story. So we can take a look at the public API of the byte array type. And here I just did a little code that picks all these methods that do not start with double underscores. So I ignore the special methods, and I display a table, and I'm just running through and doing a column print, which I had given you guys the code of above, and I sort these API names, and I just display them in 5 columns in this case, which is the default number of columns I think I used in the implementation of column print. So we have 48 names that are in the public API of the byte array class. So you can see it's a lot of stuff. We have replace, just like in string, our partition, and so on. We got pop. We have insert, just like in a list. So looking at the methods in the public API of the byte array type, we can notice that there are methods that are common to the string class's public API. So let's actually figure out what's common between byte array and string. So I got the string class here printed. We can actually do a visual, representation, but it just takes too long to write. So instead, what we do is we just take a set, convert the byte array public API to a set, take its intersection, get the common API, and print that. We get a lot of things that are common. 37 of these names are common. So what about the byte array and string? So here we have the. Am I doing the same thing here? Oh, here I'm figuring out the difference instead of the intersection, like I did here. So let's do that. So attributes byte array has, but string does not have. There are 11 of these. So we have an append, reverse, clear, all these things, insert, decode, pop, remove, extend, that are going to modify a byte array. Of course, the string wouldn't have these because it's an immutable type. So these are attributes that byte array class defines that the string class does not. Since byte array is mutable, it has append, clear, reverse, insert, pop, extend, and the other ones, just like the list class. So what if we reverse the order of the difference? So whatever string has that the byte array does not have, string has case fold, encode, format map is this one, and so on, that byte array doesn't have. So with the above demonstration, I want to see how we can take advantage of Python features to help us learn the language. We did not do anything complicated, but we programmed functions that would help us lay out certain facts in a usual appealing fashion by printing these tables out and all that. We can certainly write more compact code for this, but I'm reserving this for a homework question possibly. So let's manipulate a byte array object. Here I have list of bytes, A, B, C, D, F, and I can take the ordinal value of character star and place it in the fourth position. So here it is. In fourth position, I have star now. I can take this. So we have ordinal value for a character D is 68. I can set that there, and then I would have D at the end, the sixth position. So I can also do this with an ordinal value. So I'm essentially doing an ordinal value replacement. So it will show me the character matching that. So you can do 55, and then I get, you see there's no representation of it here. So I'm going to get an FF, which is 255. That's hexadecimal. Well, when I go to 256, I get a problem because I'm going, beyond the range of two-digit hexadecimal representation that runs 0 through 255. So bytes are only 8 bits, so I cannot represent the 256 with a byte. So then I can pop the last character, append 100, which is D, you see. So I can just play with byte arrays in a mutable fashion like this. Next, we're going to talk about regular expressions. Very, very powerful stuff. Very, very powerful. So in the real world, string parsing is in most common programming languages is handled by regular expressions. These are not verbose, but wow, are they ever hard to read, at least until you learn the syntax. Even though regular expressions are not object-oriented, the Python regular expression library provides a few classes and objects that you can use to construct and run regular expressions. Regular expressions are used to solve a common problem. Given a string, determine whether the string matches a given pattern, and optionally collect substrings that contain relevant information. They can be used to answer questions such as the following. Is this string a valid URL? What's the date and time of the warning of all warning messages in a log file? Which users are in etc password are in a given group? What username and document were requested by URL visitor typed, and so on. So there are many similar scenarios with regular expressions where using regular expressions would be the perfect choice. Many programmers have made the mistake of implementing complicated and fragile string parsing libraries because they didn't know and wouldn't learn regular expressions, which is really sad. So we'll talk about regular expressions. So matching patterns. So you should check out these things all picked especially for you to look at. So we need to import from regular expression module or library, check pattern match. So we can just run match. If there is a match, you just print the match. Otherwise, it prints no match exists, and in either case, return the match object. So we have cook as a string, and the string. So that's the pattern. Then I have I love eating chocolate chip cookies. So if we do a match, we see that no match exists. So let's take a look at this. There isn't a whole lot actually in the help. But you need to realize that it tries to apply the pattern at the start of the string, returning a match object or none if no match was found. So here is cookies are nice. So cookie starts with the substring cook. If we do a match, we get a match. Get a match object. It says that the match spans from 0 until 4. So the first four characters, a match is cook. Well, if you can do a find all, we'll be returning that we have a match, a single match. But let's see, we have good cooks make good cookies, and do find all. We're going to get two cooks because it's going to match the pattern we're looking for. We can do a search. Well, this time actually we find the the occurrence of the pattern cook from 5 to 9. Of course, last until 9, but doesn't include index 9. So the RE search method found the substring cook between characters at index 5 to 9. So that's called the span. So we used a row string literal R cook to find matches in an input string. The real power of regular expressions, however, though, comes from using wildcards to create general patterns. And here's another page. So everything that I have given you guys in this lecture and other little lectures is not just for you to simply check out, even if I wrote that you should check these out. Check out means you should just study them. So I pick these things carefully. I don't just simply throw these links at you. So you should be reading these things. So anyway, so here are some rules. The dot character matches any single character except the new line. So we have CO single character, K match any single character, E, and we look at the group of things that match. So we have cookie matching this. We see this pattern. I can replace the first dot with an O, K I E would match this. Then I have C anything anything E. What's C anything anything in here? We have cope. So C anything anything E. So we have C anything anything E as well, but it just searches for the first one. If we do find all, excuse me, so we would find cope, clue, cree, col, site. Every single one of these things that would start with C and ends with an E with two characters in between. So we are looking for 4-character words that start with C ending in E. I don't care about the intermediate 2 characters. If I use the star, it means any number of repetitions, including 0. So then followed by K. So what do I have? I have crew. One moment, I have a K in there. Why do I have a K? So I have cope. So I have the whole thing actually. It's this, it's the single, part of this thing. Let me see. Now we have something funny in here. So this thing says start with CRE, match any number of characters in between, and end in a K. Well, here at the beginning, I have CRE. Sorry, I start there. I go until I find a K. This one, yes, right? The K of Coke, but it keeps going until it finds the last K, because it's the scheme works aggressively. And since there's actually a word there that I'm not remembering right now, so it goes until the last one. It doesn't just stop at the first one. It goes until the last one. So it just went all the way until the K of creek. So that's why it stopped there. So everything in here is included. So this is the part that matches this pattern. That's why I got this whole thing as a single string. Now we're going to look at we're going to go through these words, and we're going to look at whether there's a match with CR anything any number of times ending in either a K or an N. So crew matches CR this, doesn't. dash means doesn't. Cope matches this. No, there is no CR. There is CR, but crew doesn't end up in a K or an N. Cook doesn't. So we have a CRE. Yes, CR. Something something in between the dot star, meaning a single character, including no character, repeated 0 or more times, ending up in a K. No match, no match. There's crook, there's crack, there's Croatians. It starts with a CR, ends up with an S. But the thing here is that it doesn't match Croatians in full. It stops the match at N because so it goes until N, and then the pattern is satisfied. We have a CR. Anything in between ends up in an N. So the match string or substring is Croatian, not Croatians. Cranes goes until cran, you see, and then we don't have any other match. So in this example, we check whether each word in the input string match the pattern CR dot anything ending up with either a K or an N. So this pattern says the string must start with the substring CR, then the string may have any including 0 number of characters after CR, but the word must end either in a K or an N. Note that in some cases the entire word matched the pattern, and in some cases it didn't, like in Croatians and cranes. So /W pattern matches a single letter, digit, or underscore. So we are grouping these things also. We are using the group operator here. These are not going to be matched, so I'm going to be getting these things matching in groups. So I got cookie is the match, and if I look at the groups here, I have OK and I, because this part would be OK, this part would just be an I. So I just wanted to match. So I'm just grouping the matches. The whole thing would be cookie, would be matching the this part because it ends in an E. So S would be, actually I can just do cookies are wonderful. And it would be the same thing because I would be matching up to here because it ends up, this pattern ends with an E. And it doesn't go until here because you need to have C something 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 ending with an E. And the thing is, it matches any single letter, digit, or underscore, so it would just stop before that. So I have a single thing matching here, you see, with a K right next to it. So K would always be here if there is a match, because K is just one-to-one match. /W would match a single digit again, a single letter, digit, or underscore. So one character. So I cannot go until this E. There is nothing that tells me that I can just keep going because I don't have this star, dot star, or anything like that. So it's not an aggressive match. So I have CO matching from direct match here. Then I need to match another character followed by K. So that would be O, and I group the two, so I would get OK. And then I need to match another character. I group that as well, and then I need to finish with an E. So I cannot keep going. The /W pattern matches a single character that does not match the other one, /W. So let's run that. So we have, it's not a single letter, digit, or underscore stuff. So I would be matching Coke, but this, at sign would match. With cookings, I need to end up with any character star, so represented, this is lowercase, of course, any character matching, ending with a G, so the S would not be included. So then I would start with a C, any number of these things, and then ending up with a G. So I would just take the whole thing. The S pattern matches any single whitespace character, which includes a regular blank, excuse me, new line, tab, or carriage return. So eat, anything space, cake. So single space would match, no problem. So just match the whole thing. Uppercase S matches any single character that does not match /S. So I have cookie something, cook something E, right? Well, it would match I, because I is not a space. /T matches a single tab, so just matches one-to-one. /N matches a new line, /R matches carriage return, /D matches a decimal digit in the range 0 through 9. So I have C, a digit, another digit, KIE would be COO, would match definitely, because those are digits. Caret would match the beginning of an input string. So if the beginning of the strings, if the string begins with eat, so the beginning of string is not actually a string. It's the beginning, the abstract beginning of the string. So it's not going to match anywhere, but it needs to have the thing that it needs to match at the beginning. So actually, I can copy paste this thing and then say, do you want to eat a slice of cake? Right? And let's just say that the word eat must be at the beginning of the string. Imagine if it would meet. Well, actually, let's just get rid of this one, run it. Well, we would get none. So if we say it is none, we should get true, because we're not going to get a match, because eat is not at the beginning. But if we just simply searched for E without eat having to start from at the end, you would get a match, you see? But eat is not at the beginning of the string because we have do. The excuse me, dollar character matches the end of an input string. Again, there is no it matches the end. It doesn't match the last character. Okay? That there is an end, so you can match the last character and then would be the end of the string because there is nothing else. So I would see. So here I would. So this would match a string that starts with eat at the beginning. Anything in between, then it ends up with cakes is the last word right before the string ends. You see, so they would match. The square bracketed format would match any single character in this range x2. Also, I mean, it doesn't have to be a range. It could be a range as well, but it could be. It's usually a list of characters. So A, B, C would match A, B, or C. X, Y, 1, 2, 3 would match character X, Y, 1, 2, or 3. A through Z would match all lowercase characters. This is a range definition, and here is the uppercase range definition. Here is all the letters and the character and the digits. Lowercase A through the Z, uppercase A through Z, and then 0 through 9. If you have a caret, it doesn't mean the beginning. It means don't match anything other than these. So match anything other than these. So it negates the match. So not A, B, C. So anything that's not A, B, or C would match. So I'm searching for a number anyway. It says it should be something between 0 through 6, 7 through 9. So 0 through 6 and 7 through 9 would match these two. So I would be matching. So I would say number should not be in the range 4 to 9. Well, 0 should match because it's not in the range. 1 also should match, 2 should match, 3 should match, 4 shouldn't match because it's no match actually. I should be using is none. The /A pattern matches only at the start of a string. The /C pattern matches only at the end of a string. The difference between caret and /A and between dollar and $Z is explained here. So here is I have the beginning of the string, then I have anything in the range B through E, and U, and then followed by UKI, so cookie would match. Alternatively, you could just do the caret, just like we did before. Now we have a multi-line string. Simplicity is the ultimate sophistication. This is a quote by Leonardo da Vinci. So do we have this string matching with simp anything in between, ending up with an end of line at the end of the, or actually, ending up with an end of line. But that would always be at the end of this given line. So would that match? Yes, that would match. If I do the caret, would it match? It would also match. But it would, you see, it stops at ultimate and then /n. So after ultimate, I don't have any space. The string goes to the next line. So there's a /n. And same thing for the second one. Do I have the string ending up in Vinci or Vinci? Yes, I do. And it just matches that. And what if I start with simp and then go finish the string with Z? So there is no match across multiple lines, so that would not work because I'm going to get a none. If I do a dot all, now I would match the whole thing with the end of lines as well, as you can tell. If I use a caret and $, it will also match. If I do start sophist and go until the end of line, that sophist must be at the beginning of the line, or the beginning of the string. Well, it starts here, but it's the second line. It's not the beginning of the string. So that wouldn't work. I would get a none. But if I do a multi-line, turn the multi-line on, this means that I can check whether any single one of those lines start with sophist. Then it would work. And since that's the only word on that line, they would match. Well, if I do a multi-line with /A and /Z, that wouldn't work. But if I do, so there's a da at the end, which is Leonardo da Vinci. Since that is doing a dot all and then also use multi-line, I need to. These are bitmaps, so I have to or them using the bitmap operator. Then that would work as well, and it would the match would end with the dot, which is the last thing here, and then the end of line. The / character is an escape character that's used to override the meaning of a special character. So to escape special characters in order to give them special meaning. So / means just literal slash. Slash open square bracket means literal, open square bracket, and so on. But then /n, /t, /r designate the characters that we mentioned before. So this example checks for backward slash in the string instead of /t due to the slash used. So it's only checking for the literal slash. And you see we have that because we're just checking for this slash. Since this is a raw string, I use slash slash to escape it. I'm going to be checking. So this pattern treats slash s as an escape character since it lacks another backward slash at the end of at the start of slash s to cancel the meaning of slash. So, but it would be using that. So we have back tail. So because you have back space tail, so this would not be treated as a slash because the slash s would escape s, which means it would have its special meaning. Now, then we have repetitions. A plus matches one or more occurrences of the preceding pattern, whatever it is. So CO plus means O one or more times. So cookie, like the really long cookie, would match. So as long as we have one O character, a match will happen. If there is a single, it would match two because it requires at least one. Double two, double cookie, and the real actual word cookie would match two. Star, as we have talked about before, would match zero or more occurrences. So I have CA star O star KIE. I don't have to have any A, and I don't have to have any O actually, or I can have the mixture of the two. So any number of them, right? So I can just give you guys another example here. I have to, so I don't have to have an A. So cookie doesn't have an A. I have multiple O's. I can even have CKIE that would match as well, which means I have seen no A, no O in between C and K. No problem. Zero occurrences in both cases. A question mark will match the preceding pattern character occurring zero times or one time exactly. Either it will occur none or it will just occur once. And so we have color with a U. So this is the British way of writing, which means I can have U or I cannot have U. Either I will have it or not. That means so they would match. So I can also match the English or the British spelling or color. Parentheses group matches, they don't match anything themselves. So this is used to extract different parts of an overall match. Then we have a way to check for specific number of occurrences. So if you have an integer value n, it will match exactly that pattern n times. And comma means match the preceding pattern at least n times or more. And m and comma m means match the preceding pattern at least n times, but no more than m times. So I'm going to match a decimal, slash d means decimal, between 3 and 8 times. Okay. So they would match because we have, I think, 8 there. 832 would match because we have 3. Then we have 5 matching 3 times exactly, followed by a dash, then 7 matching 6 times. Perfectly matching. Here I'm grouping actually. I have a group here because I just want to get the area code, let's say. I want to match, but I'm just only interested in grabbing the area code. So the match would just go, but you see I'm matching a literal open parenthesis, a literal close parenthesis. But my group, I'm sorry, I'm not grouping here. So I'm sorry, I'm not grouping here. I'm only looking at a 3-digit match in between a literal open parenthesis and a close parenthesis, and then dash 3 digits, and then 4 digits after the dash. That would match. But I can actually even group. You see here I'm grouping. I'm also grouping the first part and the second part. So I'm going to get 3 different groups. The first group will have 392 in it because it matched the the digits in between. So it matched the beginning open parentheses. I don't care about that in the group. I could just take the group operator outside that. That would be fine, but I don't need that because I'm not going to do anything with the open or the parentheses. I would have to get rid of them anyway eventually. So I just put the grouping operator inside the literal match. And you see it's here before the literal match ends, and then so on. So I just get all the numbers out of my phone number perfectly. But to get the groups, we have to call the groups method. So you get all the groups separately. Group just gives you the whole thing. Groups gives you everything individually. So suppose that we get a confirmation code as SMS that starts with G followed by a six-digit number. If we just need to enter the number part and ignore the preceding G, which is what you get with Google codes, we could only grab the number part like this. So you have this G and then six-digit number. So, well, we can say that the whole thing should start with a G followed by a dash, and then we have grouped 6 digits. But I'm only interested in this grouped stuff. The rest will just match, and I don't care about knowing what it matched. But since I know exactly what it's going to match, what it's supposed to match, I don't have to get that back. I'm only interested in the number. So when I get the group, I get that. When I get the groups, I get a tuple with a single value, which is the six-digit number is a string. It's quite powerful. Now we only want to the username and the domain from each email address, so we're going to match email addresses here. So I have A through Z, A through Z dot, because I can have dots used inside the names. Actually, we can even allow digits, but I'm not going to include that here right now. Actually, I can just do that as well. But anyway, let's just get this going. Then I will just do that. And then this is how the string should match. Should start. And I'm grouping the username, then an @ I'm grouping the domain or the rest, which could have any A through Z lowercase dot repeated a number of times, followed by a dot. Then you need to have at least something at the end, at least one character or more. Of course, this is not perfect, but it just gets us there. So here are some test cases. So when I run these things through, I can get I get all the matches. Username is this, domain is that. Let's see here. So Terry Jones first. See, it all matches with all kinds of because it's dots inside. But when I have hello.com, hello@.com will not match because we have to have two parts here. A part followed by a literal dot followed by another part. So it has to have two parts inside the domain. So it has to be like something like Hollywood.com or sunexample.com dot something, but only if one of the dots would be taken, would be represented. The remaining parts. So the first part would be we could have a dot as well. You see, so that could repeat as many times as needed. So but so the second thing would match because this .com tells me it just matches this part, and since this is indicated with a star, it means it can match. It may be an empty match, which means there's nothing there that matches that. So the second part would match. But of course, as I said, this is not perfect. Just to demonstrate the idea. So then we can see the groups will match in Hollywood.com. That would be the last thing anyway. You could put in, we could put in 0 through 9 here and then use digits as part of our names as well. No big deal. So that's really about the regular expressions. I've given you guys all the rules, all the fundamental rules, and I think this is it. But using all these things, you can create really crazy patterns that would match a lot of things in general. And that's the whole idea about regular expressions. You are expressing matches or patterns in a general way. General doesn't mean general meaning like match the beginning of the line, I need two characters at the beginning, then any number of characters afterwards, ending up in this and then followed by that, and so on. Next, we're going to talk about file system paths. For portability, we should always use the methods provided by os.path to process and manipulate file paths. So let's just create a relative path by combining dot subdirectory, subdirectory, and then some kind of file with an extension. So you would get that path with forward slashes in it. But of course, if you are using Windows, which you should never use, in case, you would get these things as backward slashes. So then we have this really strong path library. Instead of using OSPath and all these things, you can just simply start the path, calling the path class, create an object, and then put the other ones using slashes, just like we would when we were writing paths in Unix-based system. And then this would just create the path for you. And there it is. Do I need these? Shouldn't need them. So this is really nice because I don't have to make any calls. I just create a path at the beginning, and I add the strings. These would be the subdirectories, subdirectories, whatever at the end, ending up with a file with an extension. We can then call on path absolute to get the absolute path of the above relative path. We have the book example here. We have changed the or modified the code to show a few other things. So we are importing from the path list. So count the S location. Let's see here. So I have a bunch of files. So let's just see. So we're going to run through all file entries in the current subdirectory. So how do we do this? We get the directory path, and then we do an iter directory. Iterate over the directory entries. So for each path, we check if it starts with a dot. If so, we continue because those are the current current directory entry, the dot dot, the one above the current directory entry. So if the path is a directory, the current file entry is a directory, so we descend down to that path recursively. So we call ourselves recursively, and then keep adding to the variable that we're keeping at the beginning, and then we continue from here on out. We don't keep going because we have a path. So if the path suffix is not .py, we continue. Otherwise, we would be processing the source file. So we open the path as a file. For each line in the file, we strip the line. For if we have a line, and if this line does not start with a hash, which means it's not a comment line, we increment the S location or number of source lines by 1. And then we return that value. So every single file we process, we're just going to print out here anyway. So we create a path, that's the root path, and then we call count slog on this root path to get the number of lines of Python code. Actually, I don't like this slog. But anyway, because it doesn't. I should change this name. So count. It should be more like this. Count Python source lines. Source line 0. source lines there, count Python source lines, was it? Yeah. And then source lines. Can you call number of source lines? Oh, okay. I'll just without that. And then let's see here. So count Python source lines. Okay, let's run this. Oh, I have a little mistake. Let's see. slog. I use slog. I use another slog. So this. Ah. All right. So I'm running. So I'm just looking for all this the Python files inside my directory, in all the subdirectories and everything else, whatever I have, and I'm just counting how many source code lines I have. As long as the line is not empty. So if I have an empty line, I don't count it because I stripped the line. Obviously, if the line doesn't have anything on it, if line would not, return true, so it would just keep going. And if it's not starting with comment line with a hash, so it's not a comment line. So you may have a source line actually that's followed by a comment, so that's not going to be counted. So that's not going to be counted out. That would be counted as a source line because it is a source line. It just happens to have a comment at the end. So when we run this thing, it tells us that we have a lot of files and all that, and then we have 6,380 lines of Python code at the end. The parent path, actually display the path back. This is my path. The parent path would be subdirectory, subdirectory for this file. Well, I can also do so. I can have a legal path, but legal doesn't mean that it exists. So I can check if it exists, and it doesn't exist. There is no such thing on my file system. I can check if it's a directory, actual directory. Since it doesn't exist, it's not actually a directory. I can create another path like this, and but I can actually create a real path that exists and check if it's a directory. Of course it is, because we have it. So you can check out the help on that. Now, I got a question. If you look at how I constructed my path, I use the slashes like I did before, but how does this work? Right? It's like, it's nice, but it's like I'm using slash and it's turning it into a slash. Or what is it? What's happening here? Well, actually, you should be able to answer this question promptly if you understood how classes work in Python. Well, we have this. We get a path that starts the whole thing. It's a path object. Then we get the slash. Then we get a string object, another slash, another string object. Now, how is this any different from the division operation in the following snippet? I get x, y, z, or integers, x divided by y divided by z. Well, no difference at all. The trueDiv and rTrueDiv special methods in Python would be overloaded to do something else, and in this case to concatenate paths. We can actually write our own simplified version of pathlib path, so we can actually show how pathlib path does the same work. So I just picked the directory separator as this. Actually, I should have called this the directory separator. So where am I using it? Right. So I'm going to initialize the path to path. I'm going to just simply return it because it's a string, and I just do the same thing here for string. I'm going to just overload through div. It's as if I'm dividing, something with something else, but I'm going to be getting another path. This could be a regular path, one of my paths, in this case, a simple path object, or it could be a string. If it's a regular path, I just get the path value of the path, and then I join these two using the string join, directory separator join, and I get the path. Okay. Now, if it's a string, I just don't even care about it. I just use it as it is, as far as this new path is concerned. So, see, look at this. See, I start with my simple path, then I have slash, which would just be calling through div. I would be adding this thing to it, then I would be dividing, in a way, kind of visually dividing it with another string that would just be adding it to the end. I could actually even do the file.txt to complete the whole thing. So it's really as simple as this. I could have done the following. This one could have been another path. Simple path. Would have worked the same. You see? Because this would check that it's a path. It would just take the string version, whatever. So when we display it, I just, I would always be converting them to a string, so I would just be doing this joining no matter what. So, but see, when I do true div, I return a simple path. That's the key. I need to return that so that other people can, or others, can continue working with my path object. Otherwise, I will be returning a string. Yes, the path is a string, but I actually represent it within a path object, a valid path object. Oh, actually, the path is valid inside the simple path object. So, here I showed a different example would be working the same way. And actually, I can do the simple path and provide file.txt. I'm not checking for certain things. I could use like slashes inside these things. It would look ugly and it would be incorrect. But anyway, we're not doing that much. We're not doing any error checking here. So this / is basically just syntactic sugar that activates the true div on a simple path object. It's just like that. The book doesn't mention these things, so I just thought I expand upon it so that you can make sense of why these things work like that. It's beautiful, but you should also think about how it works. Next, we're going to look into serializing objects. When transferring data over a network, we need to have a way to format our in-memory data so that the recipient can reformat the data and create an exact duplicate of it at the other end. We can devise our own method for transferring text or binary-based data, but this is not very desirable in general. The Python pickle module provides an object-oriented way for storing and loading data turned from external sources. These could be files, network, and so on, in binary format. So if we take a look at the pickle module, we have all these things that we can do with it. Essentially, we have the pickle dump or dump string, or load from a string. Dumping to a file, loading from a file. So we have some data, which is a list. I get strings inside, floating point value. I get a list. So I'm going to be saving the data in this pickle file. I open the pickle file, but I have to open it for writing, but I need to open it in binary mode. And I just dump this data to this file. So I will be pickling it and then doing all kinds of format conversion so I can be stored. And then I'm going to actually be loading it back using, as you see, I'm using with, so the file will be closed automatically on each open. And I need to read with binary mode, and I have the loaded data. Now, I'm checking if the loaded data is identical in value to the other data that I have started with, and lo and behold, I get the same thing. And if I print the loaded data, I get exactly the same thing as I did. See, so pickle dump and pickle load deal with only a single object. You should note that. Now you can customize pickles. So the principle of pickling is as follows: any object is pickable. Uh, I'm sorry, pickleable as long as all its attributes are pickleable. So what's unpickleable? Some data is transient, that is time dependent, and it may not make sense to pickle. For example, an object that represents a live database connection at a given time. There's no guarantee that it would make sense to restore such objects after some time because there would be no guarantee that they would still be relevant. We also cannot tell in advance how much later actually we will have to restore data from disk, for example. Therefore, we need to customize how such transient data is to be stored. So your textbook provides the following code. So we have this updated URL class. So update period is 3600. This is seconds or an hour anyway. So it just keeps an update period. Updating would mean that it would open the URL, read it, and then update the time that it just reread the page. So then we would be scheduling this update by using the timer function. So update period would be entered. Then after this time passes, the update function would be called or method would be called, and then this would be turned into a daemon, and then the timer would start. So it would just be doing it all the time. So we have the authors page. That's the updated URL. So if you wait 3600 seconds anyway, it would get updated. But actually, what if we drop that down to, let's say, 5 seconds? So let's see what would happen. You see, after 5 seconds, it's updated. Another 5 seconds, it would be updated, and so on. So if you do a dump s, or dump this to a string instead of to a file, it just tells you that you cannot pickle thread log objects and so on. So when pickle tries to serialize an object, it simply tries to store the object's dict attribute, and dict attribute is a dictionary mapping all the attribute names on the object to their values. Luckily, before checking dict, pickle checks to see whether a get state method exists. If it does, it will store the return value of that method instead of dict. So we're opening here the same way, scheduling the same way. Then we have the get state. We're just going to create a copy of this dict, and then if the timer actually is in this new state, we're going to delete it and then return this new state without the timer being there. So we're actually removing things out of it, and then calling schedule in this set state. So actually, I should check this thing to make it 5 again. So I'm calling, and this time actually I can pickle this whole thing, even though this string that got pickled into doesn't make sense on its surface, but it will get pickled now because I'm taking out something that's not pickleable and then enabling the thing to be pickled or to be pickleable. So serializing web objects. It's not a good idea to load a pickled object from an unknown or untrusted source. It's possible to inject arbitrary code into a pickle file to maliciously attack a computer via the pickle. Another disadvantage of pickles is that they can only be loaded by other Python programs and cannot be easily shared with services written in other languages. Now we have this thing called the JSON format. It's a human readable format for exchanging primitive data. It's a standard format that can be interpreted by a wide array of heterogeneous client systems. Hence, JSON is extremely useful for transmitting data between completely decoupled systems. They don't have to be Linux on both ends or Windows or whatever, so it could be any operating system. So it doesn't have any executable code support. Only data can be serialized. So it's more difficult to inject malicious statements into it. That's why it was designed like that. So because JSON can be easily interpreted by JavaScript engines, it's often used for transmitting data from a web server to a JavaScript-capable web browser. If a web application serving the data is written in Python, it needs a way to convert internal format into the JSON format. We have the JSON library for that. It provides a similar interface to pickle, dump, load, lotus, and load. The default calls to these functions that are nearly identical to those in pickle module. There are a couple of differences. Obviously, the output of these calls is valid JSON notation rather than a pickled object. In addition, the JSON functions operate on string objects rather than bytes. Therefore, when dumping to or loading from a file, we need to create text files rather than binary ones. The JSON serializer is not as robust as the pickle module. It can only serialize basic types such as integers, floats, strings, and simple containers such as dictionaries and lists. So suppose we have the following class that we wish to serialize. We got this contact class with first name, last name as instance variables, and we got the property called full name that joins the two. So let's run an example of this. So all the other things still going on, as you know. So if you look at the dict field, we have first and last. That's all we have. When we have JSON dump s of these things, we got we can display. This is the JSON string with a dictionary looking like representation of the class contents. We can load from this string and get the same thing in Python, and the type will be a dictionary. So accessing a double underscore attribute is not a good idea. In addition, what if we needed to supply the full name property as a value? So we need to write our own custom encoder for this. So we have the method checking if it's a contact type, so then it would just be separating these fields out, and then we would be calling the super default, because we need to overwrite the default of the JSON encoder to create an encoder for our class. So the contact object will be encoded manually by the code we have above. Everything else will be sent to JSON encoder's default method to be serialized. So a little note here, the particular format of the dictionary we create for contact object in the contact encoder default method has to be agreed upon between the sender and the receiver so that the receiver will know exactly what to expect. So we have C1, which is a contact object. If we do a dump s on it, but with using the class contact encoder, we're going to get the, oops, didn't run this one. We would get that. And so the above, this above takes care of encoding given contact object into JSON. What about decoding? So, so we get is contact is in there, and if so, then we just get back the first and the last fields, turn it into a contact. So we can pass this function to load or load as, so the proper contact object is created automatically on load. So here is the data. This is the thing that indicates it's a contact object right there with a lowercase true, because that's JSON's true. It's not the Python's true. And then we say that we have the object hook coming from the from this function, which will do the decoding, and then we get back a regular contact object. So we would be creating or building a regular expression-powered templating engine. In the case study, we will be parsing some given text, replace directives with text. They will be generated based on some input. Directives in the template will behave as placeholders for actual values in final output. So consider an HTML file with the following content. Here we have all these things, comments and things, and H1 titles and stuff. Paragraphs and tables and things. So we have tags of the following format, where the directive can be of the one of the following. We can say include. We can define a variable. We can define loops. We can define the end of loops, and we can define loop variables. So we have some input data. So the templating logic will use the input set and render an HTML page accordingly. So this is input you're going to use, and we have the template. You're going to place these things in the template. First, some code for processing files and getting some data from the command line. So the complete code is at this link, and I'm actually redoing this thing and then saving it somewhere else. As you can tell, I'm using the file magic here. So the directive regular expression is as follows. It starts with two slashes, two stars, followed by space, any number of spaces, followed by include or variable or loop over end or loop end loop or loop variable keywords, and then it will be continued with any space, and then anything that's not a space, followed by space, and then finishing up with star star, and then a forward slash. So you would start with a forward slash, literal star, a number of spaces. So I would have the directive like this. The directive I would have slash, forward slash, star star, a number of spaces, the directive name, space, some data, and then ending up with star star slash again. So you see I have include this HTML file, include that HTML file, loop over something called book list. That would be the name of my variable. So I'm going to be looping through individual items there, and then whatever is the next value from that list that I'm going to be looping over, I'm going to be inserting right there. Loop variable doesn't need any parameter. And here is the end of my loop. Then I'm going to include something else, and I'm going to finish. So I have my template, which I'm going to be opening. I get the working directory, starting position, and all these things. I'm opening my output file name for writing. And then I'm going to be opening my context file, so I'm loading it as JSON from there, and I'm going to get my context. So here I'm just going to be processing for now. So let's see how this one works. So we can run this with here is the index HTML, which is the template, and then I have all kinds of things I'm loading in, the JSON context and all that. Maybe what I can do is do the following. The context has this, which we talked about up here. This is my context. Context meaning essentially the input data. Okay, so when I run this, it's just going to tell me processing because we have only worked on the mechanics of the whole thing. I'm loading this data and getting ready to do the templating. So the mechanics seems to be working fine. So note the regular expression has been broken up into two lines, but it's just there to it's just express it in parts, but it's just going to be joined anyway because the parentheses around, which means that they will be concatenated. So let's take a look at this regular expression. So it has all these things. The first will match a forward slash, then would match a literal star, match any number of spaces because it's slash s star including 0, match any number of characters except for star and blank. That's this one right here. So I get a star and I get a blank. Match anything other than those. Then match a star, so any number of times, sorry. And then match any number of spaces, match any of these. One moment here, I have to go up actually. So forward slash star in number of spaces, match any of these listed keywords, match any number of spaces, match any number of characters except for star and blank, match any number of spaces again, um, match slash, actually match two, match two stars. I will fix this thing, but I cannot do it right now. And then match and end with this forward slash. So it's the explanation here. I'm not gonna, you guys can read this because I just spoken through it. So we have two groupings here. We got a grouping here, and we got a grouping over here because I want to pick the directive, and I also want to pick the parameter for the directive. So that's what I would get. In the program, the start position variable will be the index of the current character in the input stream that we are processing. The template engine process method has to find each directive that matches the regular expression and do the appropriate work with it. However, it also has to take care of outputting the normal text before, after, and between each directive to the output file in unmodified fashion. Note also that we compile the regular expression and use the compiled version. One good feature of the compiled version of regular expressions is that we can tell the RE search method to start searching at a specific position by passing the start position keyword. If we temporarily define doing the appropriate work with the directive as ignore the directive and delete it from the output file, our process looks quite simple. So here's my match. So I'm going to be based that upon the directive regular expression. I'm going to be searching the template, and I'm going to start with the start position. As long as I get a match, I output the start everything between the start and the match start. So the match start then would be updated to the match end position, and then I would go to the next match. And so I just keep on matching using the directive. So I start at the beginning here. So this is the first, and then I do the processing, I do the match, and go back and do this again. And then at the end, I just write out to the output file whatever remains. So we start by looking for a match for our regular expression starting at character 0 in our template. As long as there's a match, we do the following. We write the output file all text from start position until but not including the character where the match starts. We update the start position to the last character of the match. Note that the match will be of the general format such and such with something in between these two parts. Then we'll launch another parent search string from the updated starting position in the template string Finally, we write everything else that does not match at the end of the template string to the output file. Well, have you noticed anything missing here? Well, since we are doing incremental development, we have not yet handled the pattern that matches and replace that part of the template with what must be inserted based on the input variables. So we need to do that. So here's the final version. So we output. So we start again with the same way. Then we write that part that doesn't have any match to the any keyword or to any directive, and then we get the directive and the argument right from the groups of the match, and the method name that I'm going to call would be process the method name, and then I would do a get attribute on that method name. And I would be calling it, I would be using this as since I would be getting back a function or a method, I would be calling it with the match and the argument. That's my API for these process directive methods. So then I just go back and do the same update with the match, and then I just print out. Yeah. As you mentioned in the explanation above, in the RE experience above, we'll have matching groups of template strings. So match groups will return the two matching strings, first the directive and the parameter for that. Sometimes nothing, of course, in the case of a loop variable, there will be nothing. Then based on the directive name, we construct a method name, because there will be a method that will define with the prefix process underscore. They will process each particular directive our templating language supports. Of course, this is for modularity. That is, we really do not want to cram all code for handling all directives into a single method. That would constitute bad organization. When using Python's getAttribute function, we look up our method that corresponds to the directive we just grabbed from the input, and subsequently call that method with the arguments match and argument. Since the method we will now do, I guess, well, what to do, we'll know what to do. Oh, actually, oops, we'll know what to do in regard to the current directive. We pass the argument value, which may be different every time, so that the corresponding processing method can look up the value of that variable if there is such a need. The match object is passed along in case something else needs to be investigated in the match. The rest of the code is identical to what we already considered above. Since we have 5 directives, we'll have 5 separate process methods. So process include, we'll just say working directory / argument, because we're going to create a path. Working directory is a pathlib.path object. Again, the slash used the same way before to create. So this argument would be actually would be the not just argument. Actually, let's just call this the HTML file path. And that's what. So we'll be opening it as an include file. Then we will be writing it out to the output file. Read the whole thing, write it to the output file, because we're just including it. And then we would be updating the position to the end of the match. Okay. Processing a variable, we would be looking up from the context using get of the dictionary class, the variable. And if you don't have anything, we just return an empty string as default. And we just write that to the output file, the value of the variable. And then start position would be updated again to the match's end. Process loop over. We have a match, and then the second thing would be actually a list variable. We expect it to be a list. So we have the loop index. The loop list would be, we're going to be looking this list variable by name, getting an empty string, list if there is no such thing, and then starting position and the loop position would be updated to the match end. So this method loops over an iterable value whose name is given by list variable in the variable lookup table self-context. This self-loop index indicates the position in the list that will be looked up using list variable. From self-context, using this index, we will know what value we are referring to in that list. The loop position will tell us where we need to jump back to when we get to the end of the loop. Note that we are only grabbing this and storing a list in self-loop list based on the list variable that we'll look up in self-context. In other words, we are not writing anything to the output file. So we are only preparing the looping. You see, we need to keep going back to a certain position here. So we're gonna maybe we'll come back to this part. So loop variable. All we do is we access the loop list that we have stored here inside the object, and we're going to be looking at the value at the loop index. And the starting position would be the match's end. The loop variable directive outputs the value at the current position in the self loop list variable and skips to the end of the directive. Note that it doesn't increment the loop index because the loop variable directive could be called multiple times inside a loop. Now, this is the reason why we have, the book has constructed this thing with a process end loop keyword, which is where the loop index would be incremented. So if the loop index is more than or larger than or equal to the loop list, which means we have reached the end, we have to update the starting position to the match's end, delete all these variables from within the object, and then update the start position to the self loop position. This method determines whether there are more items in the loop list. If there are, it just jumps back to the start of the loop. Incrementing the self-loop index. Otherwise, it resets all the variables that were being used to process the loop or the current loop. Just one moment, please. So that the engine can carry on with the next match. So note that this particular looping mechanism is very fragile. If a template designer were to try nesting loops or to forget an end loop call, actually that would be represented better like this. It would go poorly for them. You would need a whole lot more error checking and would probably want to store more loop state to make this a production platform. So example of different directives here is, we have all these things we talked about, loop over. So we have loop over book list. Each loop variable value would be, it's like for each loop variable in book list. Whenever you come to end loop, you just go back to this, you go back to this, and so on. So the value would be iterated through. So it would have to be a list. So for each loop variable, the next value from book list will be inserted in the output stream. End loop signifies the end of the loop. The increments the index as we have seen. Actually, it's possible to set up a loop that should be where files that need to be included get written to the output file with an include directive, for example. So Let's put the entire code together and give it a go. The following is some print statements to make the whole thing, more easier to understand. So I just put the whole thing together like this. You have to grapple with the logic of this looping mechanism a little bit more to understand it a little bit better. Especially with these positions, but I'll let you guys do that on your own. So here we just call process. So creating the file, because I'm using file magic, and I'm just calling the whole thing here. Disregard these updating stuff. So does a lot of stuff, and then does the include and everything else, and writes the whole thing out. So I actually talk about this looping mechanism. So special interest is how the looping structure operates. The constructs have to do with the looping are loop over, loop variable, and loop. If you investigate about output, we can easily tell that once the loop body is entered, processing processing alternates between loop variable and end loop. Note there is no Python looping mechanism used in any of the corresponding methods. So how is looping really happening? The critical instance variables used in the methods that correspond to the three template constructs that govern looping are self loop position and self loop index. Loop position keeps track of the index where the input is being processed. The self loop index keeps track of which element from the iterable or list that we need to loop over. Note for a given loop, meaning loop over, the text position self loop position is initialized to the first character after loop over specification. That is, with this, we enter the body of the template loop. Besides, the starting text position from where the processing will continue, which is self start position, will also be set to the same character position. In addition, the items to be processed from the iterable or list self loop index from which will access elements is initialized to 0. After this, the loop returns back to the while loop in self-process method, and the next match is sought. For the above example, the next match will be a loop variable. The self-process method will then write everything from the end of the last match until the beginning of the current match to the output file. Next, we will process the trdd loop variable, tr, and so on. Actually, it should be like this. Oops, where is that now? Oh, there it is. This section in the input stream in the above example, note that this is the place where the code writes the current value of the list variable to the output file with the surrounding trtd or row, table data and so on. Note, however, that the loop position is not advanced in the self-process loop variable method. Before self-process loop variable ends, the start position of the next processing stage is advanced to the first character after loop variable, which starts with td, tr, the end of it. Then the control goes back to self-process method where the next match is sought. The next directive match will be end loop. Before processing this next match, self-process will write all text between loop variable and end loop to the output file, which is /td/tr. The self-process will call self-process end loop. First, the loop index is incremented, then self-process end loop checks whether all items from the self-loop list have been exhausted. If so, it will delete the loop-related attributes from the current template engine instance. If there are no more items to be processed from self-start list, the starting position of the next section of input text to be processed is advanced to the character right after the end loop directive. If not, the position where the input will be processed is set back to self-loop position, which points to nowhere but the beginning of trtd. You see? So that's why you need these indices to go back in the input string so that you can just do the replacements as many times as you need. So it goes back to the beginning of this whole thing, and so on. This is the trick that accomplishes actual looping over the input text. The process repeats until there are no more items in self loop list. In self process loop variable, we pick the element at list position self loop index and write its value to the output file being created. The start position is then updated to the character one after the current match, that is the variable directive. Finally, let's see the output and let's also render it as HTML. So read this whole explanation, please. Go to it and then investigate the whole thing yourself so that you understand how this looping mechanism is executed. Essentially, just take the loop position back to the beginning of the loop variable, so you can just keep rewriting the loop body. And so you just have to take it back to the character right after loop variable, and then write the beginning of the table entry. When you catch the loop variable again, you put your next value from the loop list there, and then since you will match loop and at the end, you write the end of the table entry slash tr slash td to the file. So you don't even have to understand what those things mean. And then you increment, but you need to go back to the beginning of the loop again, which is the character right after this loop variable directive in the input file. Then you just keep processing the whole thing again the same way. So that's how you loop, you see. Just a trick you play with the indices where you are in the input text. So here is our output file. I can't print it out. So to render, actually, we can just use an iframe and give it the output file that we created. And now it's not showing for some reason. But anyway, just did it a little while ago. So for customization of formatting, you can see these pages, also see these pages as well. So there's a lot in this, especially this case study is really cool, really nice, I think. And I'll stop the kernel here so it doesn't keep doing that. So this is what we have to learn with strings and serialization, especially regular expressions are very, very powerful, and Unicode stuff is also very, very critical. So please go through the notebook when you are going through the video lecture. So I'll see you in the next one because we have a few more to go. So I fell a little behind. I'm sorry about the videos being a little behind, but the notes were ready, so I could go through them myself. They've been ready for some time since we started doing the short exams. I have to get back to that. So, okay, talk to you again. Bye.